Hi, everyone. It's my welcome to introduce Andelle Kudzal. She's calling in from Army Research Lab in Aberdeen Proving Ground. I've had the pleasure to work with her for the past couple years, mostly in the last year through a SMART scholarship. And she's doing really great work with novel materials, developing them for additive manufacturing. So yeah, if there's nothing else you want me to say, without further ado, I'll give you the floor, Andelle.
Thank you so much, Anna. So a little background about me. I am currently the Metals Additive Manufacturing Team Lead for CC DevCom's Army Research Lab, as well as I am the lead researcher in their powder bed fusion work. And I've been working there for the past 6 years now. I started as a grad student when I was working on my PhD in manufacturing engineering and stayed on for my postdoc, and then as a materials engineer. Let's see if it moves. If not, Anna might have to take over. Oh, there it goes. Okay, so just a little background of the MateriAlZ scope at Aberdeen Proving Ground. So we're a research lab. So we have a lot of, we try to do a lot of tech transitions. So our overall goal is to help the Army. And so through that, we team up with academia as well as our the OEMs of these parts, such as Honeywell, as I was mentioning earlier, if you're here earlier. And as well as kind of the people who are in control of the overall like manufacturing things, such as the people that make the tanks, kind of the other platforms with which the Army uses. So there's a lot of focus on mission readiness, preparing for the Army of the future, and being able to include new manufacturing techniques in order to make sure that we're able to manufacture the point of command, as well as being able to modernize our systems. So how we do that is we kind of look at gaps. And so we do a lot of novel alloy design for additive manufacturing, because historically a lot of the metal used for additive manufacturing is like casting based. And so we're looking for stuff that would meet our desired uses, because we might not have a traditional use in terms of the mechanical characteristics that we need, as well as looking at the qualification certification of these parts. So being able to have a part, take it off a build plate, and then being able to put it in a, say, for example, a tank engine safely. So I work on developing qualification certification standards for the additive manufacturing parts we use. For example, I published a powder spec for a novel high-strength steel last year for additive manufacturing. So I'll look at kind of the foundational stuff we do. So we do a lot of foundational science, looking at additive manufacturing itself, the materials that goes into it, the powder, the in situ monitoring, as well as we apply knowledge to the research. So we have a lot of applications with parts. For example, this is from land systems. This part over here, which is, I believe, a pulley system that goes into an engine. I can't really get into much detail, obviously, but you can see that we were using topology optimization in order to lightweight this without losing any of its mechanical characteristics, and then kind of going into transitioning and advancing the manufacturing base. So it is an ultra durable pulley system that can be used. And so we also have to do a lot of, say, specialized characterization. For example, we do a lot of like ballistic stuff to make sure it can withstand being in a tank, even though it's not likely to be hit itself. So kind of looking at our overall research thrusts, as I discussed before, we do a lot of work with feedstock development. Right now, we're doing a lot of work with ultra high strength steels. That's what I'm mostly focusing right now, as well as high strength lightweight alloys, such as aluminum and magnesium, refractory metals, and low cost feedstocks. Since we want to be able to look at the novel alloys we're developing and see if we can make them cheaper, so that way they're more likely to be implemented in a future system. In terms of modeling and simulation, we use a lot of multi-scale modeling tools. build models, microstructure prediction models. We've a full-time postdoc on that, as well as the work that Anna Hayes does for us occasionally. She does a lot of process modeling, which is very beneficial because there's a lot of issues with residual stress with the additive manufacturing process, since there's such a thermal difference from, say, the bottom of the build plate to the top of the sample. We're looking at in situ monitoring. We want to be able to have optical, thermal, and acoustic monitoring in our systems. And we have some stuff in process to theoretically to have X-ray sensors put in to our additive manufacturing machines. So we want to be able to kind of create a feedback loop in order to look at the process as it goes along in order to improve it. For expeditionary manufacturing, we take recycled feedstock. So we take the scrap that's been used, such as RHA, and stainless steel and aluminum. And we get them powderized, and then we try and process them in additive manufacturing, and then characterize them. And we've actually been successful with taking scrap RHA, which is an armor steel, and being able to manufacture it and get similar properties to that of the base steel. And then for repairs, we're starting to get into directed energy deposition, as well as electron beam and friction stir welding. So this is being able to repair on the fly, which is most likely to be implemented in the field and theater. So kind of going into the basic additive manufacturing process, because I'm sure most people are aware of it, but this is just kind of more of an in-depth view. So in general, we start with a CAD model. And so a lot of the stuff we're actually manufacturing for the Army are fairly old. So they might not even have a CAD model. We have basically a drawing that we then have to put into CAD. And from that, we actually try and make some adjustments so it's actually manufacturable. So additive manufacturing, since it's a layer-wise process, isn't that friendly to massive overhangs or really sharp corners. So we try to add it so we can reduce the residual stress with manufacturing, as well as reduce the need for a significant amount of support structures, so it aids in the overall manufacturing process. So from that, we generate an STL, and then we make some adjustments to that, like I was saying before, decreasing the overall corners, reducing overall residual stress might be implemented. We make a build plate, and look at the processing parameters input, and then we import that into a machine, and then we manufacture. And we also have feedstock materials, so we have a large suite of feedstock characterization, such as particle size, morphology, looking at the movement of it with potentiometry, as well as in situ monitoring. So we have a lot of the machines, we have what comes with it in the package when you buy the machines for in situ monitoring, as well as we have a full-time employee who is working on inputting more novel techniques and doing machine learning in order to kind of get a grasp, as well as the monitoring system to kind of get a grasp of the process itself. So that way we can generate a feedback loop. So we can adjust the processing parameters or adjust maybe the geometry in order to further improve our manufacturing process. And so from that, once we take the build plate out, we usually have a suite of processing, post-processing, such as stress relieving, further heat treatments, or machining to get rid of supports, or maybe machining in holes and stuff like that. And so here's, for example, some look at some of our process design. Here is a cable guard that we were able to make a lattice structure for that actually reduced the need for it to have any support structures and allow it to be kind of freestanding as it was being manufactured, which greatly reduced the overall manufacturing time, as well as lightweighted the product itself. So kind of the types of metal additive machines I have in my lab, I kind of separate them into 4 different categories. So we have powder bed fusion continuous wave. So this is more your traditional metal additive manufacturing, where you have unsintered powder, and then you have a laser that's moving continuously in a scan direction. As well as we have a Renishaw 400, which is a pulse-based powder bed machine. So it has the same kind of mechanical quality of using a wiper blade in order to add more layers, but instead of being a continuous wave, it is pulse-based. So there's an extra layer of first order processing parameters that you have to worry about. So instead of just worrying about the speed, the power, and the hatch spacing, which is the spacing between single layer scan lines, you now have to worry about the speed being split into two parameters, which is the dwell time, the length of time that the laser is on for, as well as the distance between these pulses. So it creates basically a different type of defect set that we now have to deal with. We also are moving into larger scale manufacturing with the directed energy deposition. So that is where you're able to build layers on top of itself without a powder bed, and the powder is blown into the laser itself. So this usually has a much larger width, and you use a larger powder particle size, and you can create larger objects. And this is actually really good to be used because you can have several parts on the same build plate that don't have to be built at the same time, as well as you're able to use this for repairs easily in the field. And then we have an E-beam, which uses a lot of sintering techniques, because then you kind of have to make a electron beam, and then you have the sintering of the powder itself. So we're able to use this for maybe materials that are more sensitive to thermal changes, such as tungsten. So our current capabilities at the Army Research Lab in terms of additive manufacturing machines just based in metal, we have an EOS M100, which is a very small scale research level machine. We have an EOS 290 that's actually being installed this summer. So that'd be a new fun toy to play with. We have a ProX 320 that is mostly used TIE 6.4. A Renishaw 400, which is the pulse-based laser system I was mentioning earlier. An Arcam A2X. That one we're currently running Inconel on. And then we had a ProX 300, which was our workhorse for several years. However, that was recently retired and given to the University of Arizona. So now it's your guys' problem. For directed energy deposition, we have an RPM 222, as well as we're getting a future machine in fall 2021. So the goal of our future machine is to be able to use it for alloy development, because it's going to have multi-hoppers that we can put different elemental compositions. So we should be able to control the overall alloy on the fly, which is not currently capable in our RPM 222. In terms of material and mechanical characterization, we have a full room completely dedicated to powder characterization that has different types of particle size, whether it be laser-based or image-based, be able to do morphology, powder rheology, and we have SEM, EBSD, XRD characterization for that, as well as ONH, because we do worry about oxygen pickup during the manufacturing process. We have post-processing, HIP, heat treatment. We're getting a new furnace completely dedicated to our additive manufacturing builds, so we can have a faster turnaround for stress relieving. Machining capabilities, mechanical testing, Charpy, hardness, tensile, even your more obscure ones like Hopkins bars. That for us, not necessarily in general, as well as what we're very lucky to have is defect analysis in terms of having easy access to microscopes, SEM, as well as micro CT, as I'll discuss further. So with our CT systems, this allows for an easy non-destructive evaluation, which is very beneficial in the processing parameter development process, because as you have, like, say, 90 samples, because you're testing out a wide array, it takes a lot of time to, say, cross-section, mount, and polish, and then optically characterize these samples to look at the defect analysis. With CT, we're able to do one sample in like under 30 minutes, if not less. It's obviously dependent on the material choice because it's density based as well as the overall size of the object. So we have two systems. We're actually getting more. So we have a large scale North Star 5000. And so that one actually has a room all to itself, and we're able to look at very large parts. And then we have a Zeiss Radia 520, and that is used for our smaller scale. So that's the one I use, and I use that generally for the process parameter development or like looking at mechanical test specimens. So kind of getting into CT and the benefits is a case study of as we were transitioning a high strength steel from powder bed fusion, like the 320, to a DED, we noticed while we're doing our non-destructive evaluation that there's large gas pores in this DED part. As you can see here, these very large circles is usually entrapped gas, and usually that entrapped gas, historically speaking, is from the powder itself. So we previously, before we put this powder in the machine, we tend to do a full research suite where we look at the particle size, the rheometry, the morphology, just so we can see when we retest when it's used or when we get a new lot that it's consistent from lot to lot and meets our specifications. So from microscopy, as you can see from this single image that I took when I did microscopy on this a few years ago, you're only seeing like less than 20 particles at a time. Obviously, this is dependent on the magnification that you use, as well as the amount particle size of the part itself. But from this, we can see there is some particles that have issues. However, it doesn't look like it's a great amount. With CT, we're actually able to see large amounts of the powder and actually go through the powder and see kind of like the volumetric, how much of the volume is defects. So with CT, we're actually able to visualize a larger amount of internal powder defects non-destructively in a time faster than it would be to mount the same amount of powder and investigate it. But the issue with this, in terms of segmentation of micro CT images, at least with the software on hand, it's a little bit harder as a person doing it, is being able to segment the actual particles itself. So our goal with this project, the POC of which is Brett Deal, I just did the CT work for it, was we're looking at trying to add CT to our powder characterization data set in order to look at the particle size itself, the morphology of the powder, as well as internal defects. So he's using kind of his MATLAB codes in order to have instances of determining the boundary of the particles and segment it, which is harder to do with the software that I use. And then he's trying to be able to characterize the powder itself as well as looking at individual defects within the powder and characterize the defects with relation to the powder that it is within. And we're trying to have that for all of our powder sets, so that way if we're seeing large amounts of, say, these gas defects, we're able to link it back to the powder. And then going on from the powder itself to the final AM process, this is going back to what I was discussing before, the benefits of having CT in addition to like optical microscopy characterization of the overall laser processing parameters is that this on the left right here is just a single XY slice layer within one of my latest processing parameter development for high strength steel on the Renishaw. So you can see it looks pretty much, there might be like a small defect over here, nothing really big. So if I took a single layer like that and just happened to reach that layer when I was optically like looking at it, I would think my material was doing great. However, using CT, we're able to see in the Z direction of the part, and we're able to see at another slice, there's a couple defects that are, I'd say, of significant size. And what's interesting with the pulse-based laser is when you have these types of defects, they're actually circular around the pulse, and so it's a little different than continuous wave, which would be elongated along your melt pool track. And with this, we're actually able to see the full part and see, oh, wow, this actually has a lot of defects in the Z direction. So this is looking down still X, Y, and this probably would not be a processing parameter we'd want to go through in the future. Not to detract from doing optical characterization, because it's still beneficial, since with CT, we are limited by the voxel size, which is usually limited by the size of the object itself, as well as the density of the object. For example, this high strength steel is at the very edge of what is usable density-wise in the machine, so I usually have to hit it with the full height or the full length of the wattage, as well as it takes several seconds per image. Well, if I did it on an aluminum part, I would be able to get results like in the third of the time. So going into the analysis of CT, there is kind of an issue in terms of we use CTAN, which is a bitwise analysis software. So what that means is it basically takes the CT image and then it turns it into a black and white image. But it has to go through kind of like a process with which everyone kind of does the adjustments to the bitwise image a little bit differently. So you can see here, this is actually a paper from Christian Gobert, who used to work with us, but now is a PhD candidate at CMU. And so he took 4 different users of the CTN software and had them generate bitwise images from a single part, as well as gave them 4 different parts. And so he was able to see there was a slight difference in terms of the overall individual defect analysis, and that you can see here that the geometries surrounding this defect are a little bit different. However, overall, there wasn't such a huge difference overall, like porosity volumetrically measured. And so then he used a machine learning algorithm in order to generate porosity segmentation. And so we're trying to utilize that in order to kind of have a standard one kind of way of doing this, so that we can kind of reduce the overall just kind of like influence of an outside user, to have some consistency. Moving on, this is just some of my previous work that Anna is actually going to be helping me finish up this summer. This is the work into local tailoring of process property relations within 17.4 stainless steel. So for this, we're looking at being able to utilize the ability that we have an open like manufacturing system, so we're able to control the first order processing parameters among many others, like the speed, the thickness, the hatch spacing, the power on the fly. And so we're trying to see how we can utilize this change in order to affect, say, a mechanical material properties locally. So that way maybe we can reduce the need for heat treatment, for example. So we did this work with 17.4 in both argon gas atomized and nitrogen gas atomized powder feedstock. And we found that the nitrogen gas atomized feedstock had an increase in retained austenite. So this, for example, this is the argon gas atomized in an oxalic electroetchant, and you can see there's not any change in the microstructure with regards of moving inward in this part. However, in the nitrogen gas atomized feedstock, there is a decrease in grain size as we move to the center of the part. And that's because the nitrogen gas atomizing process is a austenite stabilizing, creates a metastable austenite. And then we also use this to kind of look at critical scan length. So we generated these cones of a certain length, and then we decreased them going up to the top. And we actually worked with Lance, which is the Los Alamos Neutron Science Center, which I'm sure you guys probably work with at times, to characterize the residual stress as well as the atomic weight fraction of austenite versus ferrite through the height of these objects. So we found that with laser scan length, the argon gas atomizer obviously had no austenite retained. However, there's a significant scan length, critical scan length, which if you're under actually has a significant increase in the amount of austenite retained within your part. As well as this is the one for this circular part where instead of having a regular just kind of back and forth hatch spacing, we had one that was basically concentric moving inward. And from this, we found there's a critical a position with its radially where at the very center, it had a very significant amount of austenite retained. And then we found with this austenite retained, it had a significant effect on the hardness of the object as well as on our mechanical properties. So macroscale mechanical properties, so that the argon gas atomized had a different engineering stress strain curve than that of the nitrogen gas atomized. And so this is kind of ongoing work that I'm hoping to wrap up this summer and get a couple papers published with the help of Anna Hayes, who's going to help do some process modeling on these efforts. Moving on to kind of laser processing parameter development. So this is kind of just, I don't know if anyone saw my presentation from a couple years ago, might be a different group, but that was more on single laser scans to look at feasibility. So initially, when we get a material, we look at the feasibility by generating a single line scan and then characterizing it in terms of, is it smooth and continuous single line, or is it rough and bumpy? Does it just break apart? The melt pool just break apart? And then with this, we kind of generate, now that we know that this is theoretically weldable as a single layer, we kind of look at the effect of laser scan and power. And then we generate just basically kind of like a design of experiments, but I like to add more because it's not one or nothing. It's basically need an in-between. And we try to look at a process window. And this process window is basically where can we build that we think it'll have a high enough critical density that basically will have the mechanical properties that are required in order to fulfill our project. So this is just kind of an example of what I did for AF96 on the Pro X300. Obviously, I had to hide the actual laser power and speed due to just restrictions from my build site. And you can see that for this process itself, the actual processing parameters are very narrow with which we can work with. And then from this, we're trying to also identify the process window with which we can look at maybe having different defects, because we want to, like, maybe if we want to include like a soft area for some reason in our final part requires that. So we're looking at controlling the speed and power and hatch spacing, obviously, to look at where can we have maybe a controllable defect. So this is just some from our preliminary studies. So basically, for this one, we found that we created, like, basically we had laser processing parameters. If we had to, we probably could create a small powder foam. However, if it's a larger part, it'll probably just break apart in the manufacturing process. And then we're able to, say, establish there's some recoding issues with this one, or high areas of defects, but maybe we could control, see if it's kind of erratic, it's kind of similar, then it goes high and low. So there's obviously some coding issues. Well, this one just seems all over the place. While the final part basically just has a low porosity that's continuous throughout. So we were kind of building in this defect study in order to kind of fill in this laser power scan speed kind of map. So if we had to, say, we made mechanical test specimens, we'd be able to know where to choose from. And then kind of going into the development, so that was kind of the development work for the ultra high strength steel. We were actually very successful with this. We were able actually to make one of the highest yield strength powder bed fusion steels. And this was a Air Force Base steel out of Eglin Air Force Base. And that's like a variation of one of those steels, but without tungsten. So it has a lot less more issues with, because that's like a steel that's hard for recyclability. And so this is just kind of an overall fact sheet about this high strength steel. And we published a paper on it actually last year. And we're doing more work with it now in the Renishaw 400, but we've made kind of repeatable processes on the Pro X100, the Pro X300, and the EOS M100. And we're currently working on it right now for the Renishaw 400, as well as the RDED systems. And you can see here that the actual mechanical properties for our, say, small scale testing is actually outdid that of rolled and heat treated of the same material. And the same for Charpy impact testing at room temperature. It was actually better than that of the rolled material. And at -40, it was actually fairly close. And then we had pretty good elongation at about like 20%. And then so bringing into being able to use local processing parameters or induced defects, we're looking at controlling mechanical properties of this material via design defects and local control processing parameters. So doing so, we're looking at the effect of defect geometry. So we are having the effect of, this is an ongoing study, so I don't have the results yet, but we're looking at the effect of having a round defect core or say double melting in the middle versus having a diamond shape, so something with a lot of corners that could be potential crack initiation sites, as well as the length of the defect, whether it be a couple layers, 1 layer, 3 layers, 20 layers, versus it having go through the whole entire gauge section. And we're working on feeding these results into internal mechanical models for certain properties that were needed for desired parts from our transition partners. And then getting into finally, we are starting the POC for this is Clara Mock at the Army Research Lab. We're working on directed energy deposition processing. So this is powders fed coaxially with the laser and then melted onto a substrate. So we're able to use this to create 3D parts, obviously not with the same resolution as we could with the powder bed fusion, but it's allowing us to create, say, larger parts because we're not as restricted as a build space as we are with the powder bed fusion machines. And then, as I said before, capable of building large parts, it's faster, and we're able to have a little bit more, there's a lot more laser processing parameters, and there's a lot more parameters in general that go into the DED process. So it's a lot more frustrating, I would say, than powder bed fusion, because you not only have the first order parameters, you can actually adjust the height layer to layer. So each layer is kind of individually made. So if you wanted to have more local control of your laser processing parameters, this gives you a lot more wide open uses, because you control everything on an individual layer, as well as you control the way the powder flows into the part itself. And so we're also looking at getting a new machine so we can have graded compositions or alloying on the fly, being able to use those elemental hoppers in order to locally control, say, the alloy. So if we needed softer or hardenable areas within a single part. And then, so usually with this piece of equipment, you have to do a little bit more post-processing because you have a larger part and it might be oversized and you have to machine into the final shape. And then this is actually images of what we have. So this is in our sister lab. And let's see if this video shows over Zoom. So we actually have laser process monitoring of someone full-time who's basically looking at the in situ melt pool cameras and is generating kind of a system. So we're hoping to have like a feedback loop system, not that, so we can easily modify the build and kind of say if something goes wrong, we're able to modify the build and have the data to know how to fix it. So it's something we're trying to get up and running. And then that's kind of it. And this is a cute little picture I found in one of my CT parts. It looks like a little smiley face, but the little teeth inside are entrapped powders. And these are little gas pores, and that's a delamination. But yeah, so I'd like to thank my team uh, Dr. Clara Mock, who's the one who does DED, Stephen Clough, whose presentation you saw earlier this year, Frank Kellogg, Brett Deal, Taggart, Lester Hitch, Adam Hutchinson, and then my bosses. And then that's actually my program lead holding one of our cool, this is our new icon. It says Forge the Future. So yes, any questions?
Yeah, thank you for the talk, Andelle. There's a couple questions in the chat. So I think the first is from Yoon. You can unmute yourself. Your question.
Hi, thank you for your great presentation. I'm Yoon at Electrical Engineering Department. I just started my work at ASU, and I'm actually looking for my own laser manufacturing machine for my research. And I'm just wondering if you have any experience comparing the pulse laser and the continuous wave laser for the powder bed fusion system, and especially for the processing of the ceramics.
So I haven't done any ceramics works with pulse-based laser. We have done some ceramite stuff where we basically have a ceramic with a coating on it that then is melted, and then you obviously sinter it out. In terms of the actual powder bed fusion difference, and I haven't seen, we're still in like the initial, we literally just got the machine installed in January. So we're still in the first initial characterization phase. So I can't tell you the exact difference between that and any other machine, because there's a lot more than just the pulsed laser.
Yeah.
Since every machine isn't the same. For example, it uses a wiper that is a polymer wiper as opposed to a metal-based blade.
Oh, yeah.
So it's a lot more forgiving, but I'm not saying other AM machines don't have that. So I'm still looking into seeing how it is actually different than, say, a general continuous wave-based machine.
Okay, thank you.
Okay. Next up is Bruno.
Thank you, Christine. Thanks for your talk, Andelle. Great overview of everything that is going on at the DevCon. My question is more about your experience so far with the in situ imaging, thermal imaging, and what types of information are you able to, let's say, use on your behalf, on your advantage, right? So maybe you could expand a little bit on what are some of the success stories, or what do you hope to accomplish with that so far? And a kind of a side note question is, with regards to that, is whether there's been any effort to do spectral thermal imaging as opposed to imaging at a single wavelength.
I don't know. I'm not the expert in terms of in situ process monitoring in my lab group. So we have a lot of image-based ones because we're still working on based on what usually the manufacturer gives. However, I'm sure there's some of our academic partners have done some spectral stuff, but I don't know offhand. So our overall goal is, right now, there's no easy feedback loop system, I've noticed, for any in situ process monitoring. So that's our overall goal, is have it so it actually can feed back into the additive manufacturing process itself and fix it, as opposed to going through the data post manufacturing and being like, oh, that's where we went wrong. But I think that's a lot of manufacturers' desires. It's just not there yet. Yes.
So what do you get out of the system then? Like, I understand that you're not controlling right now the power intensity or whatever during the printing process, right? But so you print, you thermally image the entire surface, all the surfaces, and then what are you doing with it right now?
So right now, we have we've been doing a lot of CT marker systems. So a lot of stuff with our work with UTEP is they have a lot more up and running in terms of in situ monitoring in their machines, because the machines we had just didn't have the internal space to put them in. So we're actually getting their data and then their parts and then CTing them and then going through the data and seeing if during the process we can see where, say, like a defect came up and then create like machine learning algorithms around that. So maybe it can predict those issues.
Okay, that's great. Thank you.
Yep. And then Andrew, we're for electron beam right now. That's still a relatively new machine for that. So now we just got a new person full time on it, and we're doing some Inconel based. But I think our ultimate goal is something harder like tungsten, something like some tungsten or tungsten based alloy, something that really benefit from having that sintering temperature. So that way it doesn't have that issue with thermal cracking like it would with powder bed, just regularly.
Okay. Yeah. When I was at GE Additive, we owned RCAM, so I worked a bit with A2X.
Yeah.
I was there doing some superalloys work. I mean, the issue with RCAM is that the company really was focused exclusively on Ti-6-4, and they don't tend to provide great support necessarily on other stuff. But
No,
I think it's actually a great tool though for superalloys. So I'd be happy to help collaborate on that kind of thing if you're interested. For refractories, we had done a little bit of work with moly and tungsten. I don't know how far that really made it though. So it's kind of new territory there. Frank Medina at UTEP had done some work for us on that.
Yeah, we actually just sent the person who's doing a lot of the RCAM work down to visit Frank for a few weeks recently.
It's a very
So,
good plan.
yeah, because they have a similar machine, and we're paying them like a bunch of money. Well, not me personally, but they are supposed to be working on that for us. Yeah, so the overall goal is like we're working with our academic partners who have similar machines as us, is they're supposed to be doing some of that development work because our team in-house is fairly small compared to the sheer amount of machines we have.
Okay. Yeah, Frank's great. If you need other people to talk to about it though, let me know. I can put you in touch with some.
All right, I'll keep that in mind, Andrew.
Okay, maybe I can go in next. So yeah, thanks for this great talk, Andelle, and yeah. So I had a question regarding the microstructure modeling. I think you mentioned it very offhandedly about that there are current efforts at the U.S. Army where we are looking at modeling some of the microstructural evolution. So do you have like, can you, maybe you're not directly involved with that project, but then can you just give us a high-level description of what's really the focus at the moment, especially in regards to additive manufacturing?
I think right now there's obviously a lot of stuff. I think you've Stephen Clough is our modeling expert, so he had his seminar a couple months ago, and he probably discussed it more in length. But I know, like right now, we're trying to not rewrite the wheel. So we're trying to gauge a lot from our what's out there commercially speaking, as well as through academic partners. But we're trying to basically integrate the material models so that way we can kind of have control over material mechanical properties without having to do all the legwork of actually going through all these different alloy systems and finding that information out manually. Trying to.
Yeah. So are you guys like looking at so things like FEM kind of models, or maybe the atomistic length scale, or or maybe phase field modeling? What are you guys really looking at in that case?
I do not know offhand the specifics of that. I would probably defer to Stephen if you want a more conceptualized process of what is in place, since he is currently my lead for that. But I know we've been out of it's been mostly academic partners, so I don't have the list of that as of right now. And then Stephen just started last year, so it's still an evolving realm. And then also with modeling, Yaltaska Anna, when she comes next year as our current smart scholar, and she's starting, so she'll have her own decision point in terms of what is going to be looked at.
That is great. Yeah. Okay, thank you. Yeah.
I had one more question, Andelle. And the other question I had is about what fraction of the parts that you're making need and require hipping?
So we honestly don't hip a lot. The most we've been doing thus far for our characterization has been just stress relieving, because you'll have not delaminations, deformations because we use a lot of EDM, electric discharge manufacturing, in order to cut, like wire EDM, in order to cut the part off. So if you don't stress relieve and you save a really big build plate, there's a lot of residual stress just due to like the height of the build itself. And so they'll basically be like 5 to 10, theoretically, a huge change within the build plate as it gets cut off that can cause the build plate to potato chip and basically just kind of ruin everything. So that's usually the most that we do. Our overall goal is, because we want to be able to, one of the stuff we're looking at is manufacturing at the point of need. So being able to manufacture it with the least amount of stuff needed. So if we can do it without hipping to close those defects, if we're able to generate parts that meet our mechanical threshold without the minimal amount of post-processing, that's our ideal goal. So hipping adds a lot of time into the overall efforts, and we have investigated it, and it does do a really good job, at least for the high string steel that we're using. And it does kind of normalize the mechanical properties. So if you're building something vertically versus horizontally, it does normalize those properties, but we try to avoid it.
Thank you. Thank you. I think that's a really important point, and knowing the status and where we are with that requirement. So thank you.
I have a question, but if anyone else has questions, feel free to post in the chat. So it's sort of a two-part question. When you're using micro CT, I think you mentioned it as sort of a work in progress, looking at morphology, but do you find that there's aspects to the defect morphology, for example, aspect ratio, that have a significant on the mechanical properties, like something outside of just the pores?
So we generally don't mechanically test something that is like, say, experimental, in terms of like trying to design, like that's the process we're at right now, is trying to design defects. But we do have, I know of, say, some Navy projects right now that I can get you some information on, that they are like, or some stuff that Penn State's doing, where they actually are trying to induce certain types of defects, like you're saying, certain geometrical defects, in order to find that critical defect shape or like size. That is something we do try and keep in mind. Is there a critical defect shape or size with which you'll still get X amount of like strength, and so it could still work? But internally, we're trying to avoid, just because we have so few people to do, and mechanical testing takes, especially with COVID, mechanical testing is like a month or two out. So that's like a future, like we are trying to use our academic partners in order to gain that information, since they have grad students. So I guess I have all the time in the world to do that.
Makes sense. And then sort of follow up on that, I think you mentioned that you'll get different defects depending on continuous versus pulsed laser. So do you find that like there's one process where you need the CT more to actually get the defect formation across the part, or like something that, just cross-sectioning won't make visible?
So with the pulse laser, I've noticed it has been interesting, because the defects are like weirdly circular and not continuous. So like usually if they're continuous, it'd be continuous throughout. However, because this is a new machine, we're still learning it. There's other like factors in it. So there's not just, you'll notice that in some parts that we wouldn't normally notice on a different machine. What you're noticing in your research is that there's flow issues across the top. And so on my latest build plate, I have all these CT specimens in different locations with the same parameters that should theoretically all have the same, because they have the same like thermal history, in quotes. But you might find that it's manufacturing right now, so I don't have any of those results, but you might find that they might have different defect properties based on the location, which is something you discovered for us. Thank you.
Yeah, of course. It's interesting to find out. And once we wrap up some of that work and comparing it to some parts that were built in a constant laser, maybe we'll see some more discrepancies and defects between
Yeah.
them. Yeah.
So you'll find, at least with all these additive manufacturing machines, every machine type has its own quirk in terms of from the manufacturer that they just kind of compensated for. And then you'll find each machine to machine might have its own quirk, which is why a lot of people, when they do the certification and qualification of these parts, you have to do the build on the same machine a certain amount of times and qualify it. And then it might not be exactly the same on a machine that's from the same company.
Thank you. Okay, so I think if there's no more questions, we can wrap up. Thank you so much for a wonderful talk, Andelle.
Thank you. Yeah, thank you, Anna, for hosting this. Krishna was not here, so I was also traveling. So
Of course, sorry, it's sort of on the fly.
yeah,
It was a pleasure to have you, Andelle.
Thank you. Thank you all for having me.
yeah. And by the way, I think we did not introduce Christina. So Christina is also one of the co-organizers of the seminar, and she is online today. Yeah, there she is.
Hey, Andelle, thank you for the nice talk.
Thank you for having me.
Sure.
All right, so yeah, let's close it and then see you next week for the final seminar we are going to have this semester. So I look forward to that. Thank you all for joining.
Thank you.